Okay, so it's 4:20. Let's begin. Do we have the recording and live everything on, Alistair?
Yes. The coffee area will be the coffee break section will be chopped.
All right. Wonderful. Okay, so we start the second and the last LISA data analysis session with Mauro PIERONI, and he is in Imperial College, London. He will tell us about the orthogonality and non-orthogonality of TDI channels. Yeah, so please screen share and tell us about it.
So, do you see my screen?
Yes, good. And we hear you, so all good.
Okay, so, well, first of all, thanks. I would like to thank the organizers for the opportunity to present my work here today. As you already mentioned, and as you can see from the title, I'm going to talk about the non-orthogonality of LISA TDI variables. This is some work I'm doing in collaboration with these people, and hopefully it's going to be out on the archive in the next couple of weeks. So this is an outline of my talk. I will start by saying a few things about detection and characterization of stochastic backgrounds at LISA in general, in the simplest scenario, meaning equal arms and equal noise levels. So I will tell you a few things about the noise model and the response function and how to compute the strain sensitivity. Then I will move on to more realistic things. So I will allow first for unequal arms and then for unequal noise levels. And I will then move on to conclusions and future perspectives. Given the audience, I won't spend much time on these. I suppose you all know a lot of things on LISA, probably more than me. The only thing I wanted to say, since I'm a cosmologist, is that for cosmologists, LISA is quite a wonderful instrument. You can do a lot of cosmology with it. And in particular, and this is what brought me to this community, you can, if you manage to detect and characterize stochastic backgrounds, you can learn a lot of physics out of that. So let's go a little bit more into data-related things. In the following, when I will say things about data, I'm always assuming my data to be in a frequency domain, and I will always assume my data to be a superposition of signal and noise here. Assuming signal and noise to be Gaussian, all the information I want is in the 2-point function, which assuming signal and noise to be uncorrelated, I can expand as just 2-point correlation of signal and 2-point correlation of noise. The latter is what we typically call the noise power spectrum. For the signal side, things are a little bit more complicated because you have the signal power spectrum, which is modulated by the instrument response. I will tell you a few more things about the response in the next few slides. But what you can do in general is to collect the response so that you define this new quantity, the strain, which is something you can directly compare with the signal. So this quantity is what LIGO people, for example, normally show in their plots. One more remark, cosmologists normally like to work in omega units, meaning they convert energies to the they normalize energies to the total energy density in the universe, so critical energy density. That's how I'm defining this omega quantity. And same thing you can do for the noise. So you can just define the sensitivity in the same units as the signal. Okay, so moving on to even more data-related things. What you need to do to achieve the required noise level is to perform some operation to get noise reduction. And this is what is TDI, time delay interferometry. Two of the possible choice you can do are the ones I'm showing here. So Michelson TDI variables or Sagnac variables. Michelson variables are typically dubbed XYZ, Sagnac alpha, beta, gamma. So Michelson is something very simple. It's just comparing what's happening along one arm compared to another one. So basically this thing versus this thing. Then you can add some extra loops to compensate for Hall effects. On the other hand, Sagnac variables are just one loop in one direction versus the same loop in the opposite direction. So very plain and simple. Actually, if you try to use these variables, what you learn is that they are correlated. So you would want to move onto a basis where your variables are orthogonal. And these are the so-called AT variables, which on the other hand, I'm dubbing with this math called AT for the Sagnac variables. And in the equal arm case, you can do this by using these very simple transformation metrics. One last variable I would want to introduce is this zeta fully symmetric variable, which is a signal orthogonal variable, like the T variable for both Michelson and Sagnac variables. I will tell you a bit more about this in a moment. So let me first tell you a few things about noise. The noise that we consider later on is basically coming out of two components. There's going to be an acceleration noise and an interferometric noise. Basically, as I will show in a moment, acceleration is going to dominate at low frequencies in most of the variables, and interferometric is going to dominate at large frequencies. Acceleration is basically related to the deviation from free falling for the test masses, and interferometric is just laser noise. What I can do is to compute how these two noise components propagate into the TDI variables. So, for example, I can compute how they contribute to the XX correlator. And what you learn is that basically you just have OMS with some prefactor, same prefactor for acceleration, and another term here, which at low frequency is just a constant. On the other hand, if I compute the same analogously, if I compute how these two components propagate into the TDI variable, I see that there are some different contributions here. And as I will show in a moment, these are going to modify the ratios between the acceleration and noise levels in this TDI variable. So if I just plot the two noise components in the left, you see that basically acceleration is larger than OMS at low frequency and vice versa at large frequency. So since in XX, for example, they just appear as these plus 4 times acceleration, as expected, acceleration dominates at low frequency and interferometric dominates at large frequency. If I expand this term here for TT, on the other hand, I get basically this factor, which is F frequency over F star. F star is the characteristic frequency of the instrument, which is 0.2 milliards, so 0.02 hertz. If I plug this factor here, basically I can see that the acceleration noise component is suppressed compared to interferometric in TT. This was also shown by Martina in her talk before. Okay, so going on to the response, the assumptions I'm using here in computing the response are isotropic spectrum and non-chiral. Isotropic means the same from all directions, and non-chiral means left-right components are the same. The response is basically has the structure. So there's going to be a factor which is depending on which quantity I want to use as the measurement. In particular, I'm using fractional frequency. Then there is a factor here, this R tilde, which is just carrying geometrical information depending on which kind of TDIs I want to use. And there is also this other factor, the W, which on the other hand keeps track of loops in the definition of my TDI variables. In this left plot here, I'm showing you the geometrical factors for different TDI variables. As you can see, for most of them, it's basically, it has a very simple structure. It's just flat, low frequency, and then it goes down at larger frequency. So basically, you can think of this as some kind of low-pass filter. The only variable which is behaving differently here is T. And you can see that low frequencies here, T goes to 0. So this is why T is said to be signal orthogonal. Basically, I have no response to the signal at low frequency. In this other plot on the right, on the other hand, I'm showing you the full response. So when I plug back all these other factors. Now that I have the response, I'm able to compute the sensitivity just by dividing the PSD by the response. This is what I'm showing in the left plot here. In particular, what I'm showing is in green is the full numerical response. In black, I'm showing an analytical approximation obtained by expressing the geometrical part as this very simple function. And in orange, I'm showing you how much the noise level changes if I allow for 20% variation in the two noise parameters. As you can see, analytical and numerical match quite well. Actually, they match within this 20% range for the noise parameters. In the right plot, on the other hand, I'm showing you again the noise, but this is going to be in omega units. So this is the sensitivity that cosmologists typically use. Okay, that's pretty much it for the equal arm case. Let's move on to more interesting things. In reality, we won't have equal arms because orbits are, I mean, along the orbit, there are going to be fluctuations in arm lengths, and this is gonna lead to breaking on the orthogonality between the different TDI variables, as I will show in a second. In principle, you can compute analytical approximations for these to test the numerical results, which I will show in a moment. Okay, let me start by explaining you what happens for the different TDI variables. So in all these plots I'm showing, solid lines will correspond to equal arms, dashed lines to unequal arms. First row here is gonna be XYZ. So you can see that going from equal arms to unequal arms is not changing much the signal response, the noise spectra, and the strain. On the other hand, when I move on to the AIT basis, so onto the orthogonal basis, you can see that T is actually modified quite a lot. In particular, this is visible from this plot here, where you can see that while T was supposed to be matching with Z, so supposed to be signal orthogonal, at some point, this orthogonality is broken, and basically it goes back, it matches with the other two variables. Z, on the other hand, here can be seen to be way more robust to corrections due to unequal arms. Similar thing happens for alpha beta gamma. Again, first line is alpha beta gamma variables. Sorry. Second line is the orthogonal combinations you can obtain out of alpha beta gamma. Again, you can see that some deviations from the equal arm case happens in the noise orthogonal variable, but in this case, this variable seems to be way more robust than the Michelson ones. So good news. Other things that are interesting to notice is what happens when I want to study correlations. So in this plot, I'm showing you what are the noise correlations. In particular, I'm showing you the off-diagonal elements divided by the on-diagonal elements, square root on the on-diagonal elements. Again, solid lines are equal arms, dashed lines are unequal arms. In both these plots, and same for the next line, they are supposed to be zero because in the equal arm case, AET is orthogonal, and same goes for AZ. And analogously, alpha beta gamma and their orthogonal variables. But you can see now that when I look at the unequal arm case, off-diagonal terms become sizable, and in particular for terms involving T in the Michelson variables, they become close to order 1. So this can be problematic. Same thing is not happening if I replace T with this Z variable, and same goes if I use these orthogonal variables built out of the Saknak variables. So both Z and these AET variables built out of Saknak seem to be way more robust than standard Michelson variables. In this plot, I'm showing you what happens for signal correlations. In this case, it seems like all the variables lose orthogonality when I go on to unequal arms. But keep in mind that for Z and for T Sagnac, T is still signal orthogonal. So the fact that signal correlations become large is not really such a big deal as in the Michelson case. So even if signal correlations are large, it's not very problematic until signal is suppressed in all the combinations involving T. T Sagnac or Z. Okay, so one extra thing I want to show you in the unequal arms equal noise is what happens if I try to attempt some signal reconstruction. So here what I'm doing is to inject some signal, just a flat signal with some fixed amplitude. This is a quite large signal. The SNR is ordered a couple of hundreds. For the reconstruction, what we use is just the diagonal elements. So we want to see what is the impact of neglecting correlations in AEZ, AET. AEZ, we know that is more or less orthogonal. So the error we're doing comparing to the full correlation matrix is not going to be huge. On the other hand, in T, we know that there could be some impact. You can see from the left plot that the reconstruction of both noise and signal is decent. From the right plot here, which is my corner plot, you can see that basically with T, I'm underestimating a little bit the error on the acceleration component. And this is slightly leading to a slight underestimation on the error on the acceleration, on the signal parameters too. But this is not dramatic. So there is an effect, but it's not something terrible at this level. What I want to do now is to switch from equal noises to unequal noises. So I want to make my problem way more complicated. I mean, this is what we will have in reality, because I mean, each test mass and each laser will have its own noise level. So this is what we will have to deal with in reality. So let's try to see how much this will impact all the discussion I did this far. So signal response is not going to be impacted by this, but noise correlations is going to be impacted. So let's first look at this. Keep in mind that for the equal arm case, both in this column and in this column, we are not expecting to see nothing for cross correlate for in the equal arm case. On the other hand, adding unequal noise levels is making the equal arm noises correlated. This is already one big difference. Second thing, when I allow for unequal arms too, the interesting thing is that basically the for all the variables which we know are going to be reasonably robust, the estimations we did in the equal arm case are basically matching to a good degree to the quantities we computed for the unequal arm case. So this is quite nice news. Finally, one last plot I want to show is, again, a reconstruction using all the parameters simultaneously. You can see that I'm still reconstructing the signal reasonably well. You cannot really see the error bands, but they got a bit larger, but not crazy larger than before. So good news. If I look at the reconstruction on the noises, what I see is that, so for acceleration noises, it seems like in some cases, AT is doing better than AZ and vice versa. If I actually look at the eigenvalues of the Fisher matrix estimated from the MCMC samples, I see that in reality, AT seems to be seems to be giving an information which is a bit larger, again, because I'm ignoring correlations. But again, this is not too terrible. On the other hand, in the P parameters, in the interferometric parameters, systematically, I always see that the noise is underestimated in AT compared to AZ. That's pretty much everything I wanted to say. So let me draw some conclusions. Equal arms, unequal arms compared to equal arms can change some things, break orthogonality. We must be careful with this. Reconstruction of signal parameters and noise parameters can be affected, but it seems like it's not too terrible at this level. Concerning future perspectives, here I did a bunch of assumptions. In principle, we would want to drop as many of those as possible in the future, take more realistic noise models, allow for time dependencies all around which are neglected. So there's a lot of work we should be doing. And that's pretty much it. Thank you very much for your attention.
Okay, wonderful. So we have 2 minutes for questions. So either write up or raise your hand. And we have Jean-Baptiste again. Go for it, Jean-Baptiste.
All right, me again, but this time without feedbacks. Thanks, Mauro, for this talk. Just a silly question. Doesn't what Quentin presented, PCI and or TDI infinity, just solve exactly the problem that you have here? Because they will account basically in the way they diagonalize their covariance matrix for these potential correlations or unequal arm length and so on.
Well, I mean, in principle, the thing is, if you use the full correlation matrix, things are going to be equivalent in whichever basis you use. So if you manage to produce something which is fast and stable, we are happy. The main thing is that if you want to do diagonalization numerically on the fly, that can be kind of unstable, because, I mean, if you look at the responses, for example, you know, this guy can become much smaller than this, and depending on the frequency, you can even hit numerical precision. So, I mean, of course, if you do things properly, everything is going to be equivalent. The point is, if you manage to make sure that everything is fine, good.
Yeah, but the thing with PCI and TDI infinity is to cut basically the parts of the space which have a very big variance, basically, so that you try not to hit those numerical stability problems, right?
But it's not a problem of variance. Here is really, even the analytical computation is going to be tricky, because I mean, when you switch from, say, let's stick with Michelson. If I want to switch from XYZ to AT, I mean, if I go to low frequencies, the difference between AE and T can be so large.
Excuse me, but I am going to need to interrupt this. We're already 1 minute past, and this sounds like a very lively discussion that merits its own discussion. So maybe Jean-Baptiste, and you can take this offline. I want to sneak in Quentin's question. So go ahead, Dr. Baghi.
Yeah, hi. Yeah, thank you, Mauro, for it. It was very interesting. Actually, very to quickly follow up on that. In PCI and both in TDI Infinity, we're computing the principal components of the either the covariance of the laser noise covariance matrix, or the laser noise covariance matrix, or the laser noise design matrix. So all the secondary noises are not taken into account in the first step. So I think we have basically the same problem. In the end, we need to have a robust estimate of the secondary noise, the non-laser noises, to do this proper orthogonalization. And I was wondering for the unequal noise level case that you investigated, like how much different were the noise levels, and could you state again what was the impact on the noise correlation? I didn't get that, I think.
So for the parameters, I generated Gaussianly all the parameters with the same mean and a variance, which and a sigma, which was 20%. So in the end, some parameters were even like twice others. So let's say mean value was like 3 and 15. Some were from 2 to 6, and some were from 10 to 20, for example. Can you say again the part of noise correlations? I'm not sure.
Okay. I mean, and so these, with this level of discrepancy, then what's your change in noise correlations? I was not sure what was the dashed line and solid lines.
Okay, sorry. Solid line are again equal arms. Dashed lines are unequal arms. Basically, I mean, what is changing is that in the equal arms, equal noise levels, solid lines are all 0 in these 2 columns. Here, because I'm introducing these different noise levels, I cannot really orthogonalize perfectly the noise matrix. I mean, I can still do it, but it's going to be different. I cannot just use the standard rotation matrix. That's the point. The interesting thing is that the unequal arms for these 3 variables seems to be more or less the same. So it seems like these variables are quite robust, even if you allow for different noise levels. The estimate you would get seems to be pretty good.
Okay, yes. So in these plots, you're not comparing unequal levels and equal levels of noise, but equal arms and unequal arms. Okay.
Correct. For unequal noises.
Yes. Okay.
All right. I think that's a good point to stop and move on.
Thank you very much for the questions and for the chance to speak again.
Good. So next up, we have Martin STAAB. Martin STAAB, he is a mature PhD student in AEI who should be writing up his thesis. He has been very productive, but he's a prized PhD student in AEI, and he will tell us about time delay interferometry ranging. So the boring 2-dimensional screen is yours, Martin. Go for it.
Yeah, thanks, Shweta, for the nice introduction. So yeah, I will be talking about TDIR that was already mentioned by Quentin earlier, and yeah, especially about the tone-assisted variant of that we came up together with Jean-Baptiste, Sam, and Bob. So I also have an introduction slide for TDI, but I will make it quickly. So basically, yeah, LISA is designed such that we only measure one-way measurements. So the 2 most important measurements in this presentation are the interspacecraft interferometer, which relates the far laser to the local laser, and the reference interferometer, which relates the adjacent to the local laser. And by connecting them, by gluing them up together again in post using TDI, we can synthesize those equal arm interferometers. And on the bottom right, you can see the first generation Michelson combination that we can achieve by doing that. And to do that, we need the ranges, which are basically the same, which are used to propagate measurements from one spacecraft to another, and those are then these delay operators. And TDI ranging is basically somehow like inverts this concept. So you're trying to find ranges that remove the laser frequency noise from your data, and you don't know them a priori. So you're trying to find them by just changing them and trying to minimize the residual power in your TDI combination. And the accuracy of that technique is ultimately limited by secondary noises in your interferometer. And this is just an overview of some more standard TDI estimators where a lot of literature already exists now, or like 5-4 papers, I'd say. So the first one is the one Tint et al. Developed. So you just take your first generation Michelson or your Michelson X and calculate the power and try to minimize this expression with respect to your delays. So this assumes constant arms. So it's basically 6 parameters that you're trying to fit. And then you can take it further and just take X, Y, and Z, so the full TDI space, and do the same thing. And you will end up with more accurate estimates of your arms. And then the third option is then what already Kantar talked about. So this PCI, where you orthogonalize those 3 combinations and also widen them. So you also take into account the noise spectra of your secondary noises. So here we're looking at the tone-assisted variant. So an idea was to inject a tone into your primary laser. So we're now in a locked configuration. So we only have one laser frequency noise that we have to cancel, which comes from the primary laser. And we inject a tone to arbitrarily increase the power of laser noise, or the power of laser noise in your measurements. Because higher laser frequency noise means you can estimate your TDI combinations or your arms better. And so you not only have the laser frequency noise, but also a sum of several tones. And we set the tone amplitude of those tones to 10 kilohertz. For comparison, the laser frequency noise is roughly a root mean square of 100 or so, 100 hertz. So it's slightly above the laser frequency noise level. And we can also see that in some simulations I was running. So in blue, you have the raw measurement, one ISI, one is a spacecraft interferometer. I think it's the one on MOSA 1.2. So you can see the wide laser frequency noise at 30 hertz per root hertz modulated with the round trip transfer function, since we're in a locked configuration. And on top of that, those 2 tones at roughly 0.7 hertz. And if you form your TDI variables now and you have an error of, let's say, 10 kilometers, then you end up with this dark red curve, and you can just see how laser frequency noise got suppressed, but not fully, since the dashed gray line shows you the level of secondary noises. So this would not be enough. Knowing the arms with 10 kilometers accuracy would not be enough. And if you just plug in 10 meters, you can see that the now the laser frequency noise is below the secondary noises, but those tones still stick out. And we can use this property to be still sensitive to to any errors in the arms. And before we would not be anymore, since laser frequency noise is basically now buried in the secondary noise. And we also formulate estimators for those cases. So first, this equation shows you the technique we use to read out the tone amplitude at a specific frequency. So it's basically just a finite Fourier transform, which is also windowed. And we do that for both tones and for all three TDI combinations. And then we just sum up the modulus squares of those amplitudes to basically also just have a value for the total tone power in all three TDI combinations. And we try to minimize this to find the 6 arm lengths. And we can do something similar to PCI, but in this case it's much simpler since you only have 6. So we have 3 tones, 2 tones and 3 combinations. So it's 6 values that we have to orthogonalize. So this is much easier to do. And we just weigh it by the TDI, by the PSD of the secondary noises. So high secondary noise means that we weigh it less into the total power in the end. So we found out that a minimum of 2 tones is required to estimate all 6 arms. Otherwise, you get degenerate directions. And you can only estimate 5 arms or 5 combinations of the 6 arms. And by introducing the tone, we get an improved TDIR performance because of this higher signal to noise ratio, where the signal is really the laser noise, and the noise is the secondary noise flow. Then to compare those 2 methods, so I'm comparing the standard summing up X, Y, and Z, powers in X, Y, and Z, and the tone assisted case here, the first one. So summing up the tone powers. I will compare in the next slide. So we just formulate our metric, so we know how good we are. So delta ij is basically the estimation error, which is given by the estimated arm length minus the true arm length, and we just collect this in a vector to analyze the statistics of this. And we find that in the standard case, we have an unbiased estimator and a covariance, which is given by this expression. And we see for higher, so T is the observation time. So the higher we choose our observation time, the better our estimates are. And as N is the level of secondary noises, and as nu is the level of laser frequency noise. So basically we are driven by this fraction. And then we have also this matrix lambda here, which just determines all the correlations between the 6 arms, and is also dependent on the locking scheme. For tone assisted TDIR, we are still unbiased, and the covariance matrix is looking really similar, except that instead of the laser frequency noise level, we now have the tone power, which is given by this expression. So we basically have another knob we can turn to increase the accuracy of our estimator. And that I want to show you in that plot. The left plot, it basically shows results from a simulation where we turn on laser frequency noise and or mass noise, and we use 500 seconds of duration to just make some quick estimates. So we can also choose that longer, and we repeat that 200 times to get some statistics, so to create some ensemble that we can analyze. And below you can see all the scatter plots, so the pairwise scatter plots of the errors in the arms. and also overplotted the ellipse that is a result of the analytical calculation. So this shows that we think we understand how all the parameters influence the estimation process. And we can see if we take the mean of all those standard deviations that we end up roughly at 5 to 6 meter standard deviation of in our estimates. If we now inject a tone with an amplitude of 10 kilohertz at those two frequencies, then what we basically find is that the correlations roughly stay the same, but our uncertainties drops quite significantly. So we now retrieve a standard deviation of only 1 or 2 centimeters, which just shows, yeah, how much better we can get if we introduce more laser frequency noise by introducing this tone. Yeah, and now I want to talk about applications of this. So there are other ranging methods in LISA. So basically there's the clock sidebands and also the PRN ranging. And yeah, important is that all ranging measurements are never measuring just the true range, but they are disturbed by several things. For example, you can have noise, or which is a random process, or a bias, which is a constant, and many are also subject to some ambiguity. So you can not determine it directly, but you have to find some integer and multiply that by the ambiguity, which is related to the wavelength of your measurement, basically, of the signal that you're measuring, and you have to determine this this integer to get an absolute range measurement. And as the best candidate in these, we have the clock sidebands, which measure the MPRs with high precision. So the limit, they are only limited by modulation noise, which is quite low. And the ambiguity of this measurement is 12.5 centimeters, which is just the wavelength of the 2.5 gigahertz clock signals. And so to use this measurement as an absolute ranging measurement, the only thing to do is we have to find this integer mij, which just adds multiples of those 12.5 centimeters to the measurement. And I was hoping that Olaf would talk about it in more detail, but this is also something we did in the paper he showed in his slides on clock TDI without clock synchronization. And there we show that you can use the PIN measurement to resolve this ambiguity or to find any offset that is unknown. And the properties of this PIN measurement show you that you have to measure roughly a couple of seconds, so 16 seconds is a rough number, to find this offset or this ambiguity. With standard TDIR, this is only, so it's much less accurate, and you can only resolve it after 6 days. So this is quite a constraint. But if you then use tone-assisted TDIR, you're back at orders of magnitude what also the PIN measurement can give you. So here we can show that TDIR can be used as a more or less equivalent fallback or complement to PIN ranging. Okay, so to summarize, this is just what I've just talked about, comparing the different accuracies of those three methods. And the big take-home message is, I think, that this TDIR can indeed be used as a fallback or complement to PIN ranging. And in the future, we want to study different topologies of the tone-assisted variant, since we think it's quite promising. So we looked at injecting those two tones in the primary lasers, which worked quite well. And in the next step, we want to also see what happens if you inject tones in the transponder logs of the other spacecrafts. Another thing is studying the impact of clock drifts and noise, since they could have non-trivial couplings if we look at the transponder lasers, and also estimate using this method to estimate other common mode delays occurring in cables or photodetectors, which is Sam talking about in the next talk. So stay tuned for that one, and thanks for your attention.
Thank you, Martin. Yeah, so we have a full-blown 5 minutes for questions. So please raise your hand and feel free to speak, which I'll moderate. Well, since Martin STAAB had his master's under my tutelage, I think I have deserved the first question. What determined the choice of your 10 kilohertz tone amplitude?
That's a good question. So we had a lot of debate about that. Oops, I hope you can see that. So I think the upper limit of the tone amplitude or tone power should really be that you're above the laser frequency noise. Otherwise, you're not introducing any more noise power or signal power into your lasers. So the lower limit would then be a couple of, yeah, good question actually, how this scales to the power spectral density, but at least you should be above, I don't know, 10 Hertz, I guess. And then the upper limit, so of course you want to make this tone as big as possible to have to get the most out of it, but there is an upper limit, and this is due to the nature of how you inject the tone. So you would have actually a backup slide for that. So you would actually inject the tone in this primary laser, which is locked to a cavity via a PDH control loop. I'm not an expert on this.
What is PDH? Oh, boundary, okay.
Yeah, it's a boundary hole. I think it's the most common method of locking a laser to a stable cavity. And the tone amplitude should be much smaller than the modulation frequency of your phase modulation you apply prior to injecting the laser into the cavity. And if you look at some rough numbers, I'm hoping I'm getting those correct. So if anyone in the audience thinks numbers are off, please speak up. So the modulation frequency is 100 kilohertz, which then is basically the upper limit, or you should not maybe. So that's why we choose 10 kilohertz, since it's just a factor of 10 smaller than that. And we hope to stay in the linear regime of things to not mess up too much this locking scheme.
I'm just giving a moment for people to raise hands or type up their question. Otherwise, I still have another question. Okay, I'll come back to you, Quentin. In slide 7, you were showing the covariance matrices. Is this a Fisher analysis or MCMC, like a real Bayesian thing?
Yeah, I think it's more closer to MCMC, but we're not just studying one realization and jumping around in parameter space, but we really take 200 realizations of the same setup and then estimate the most probable parameters and then look at the distribution of this repeated experiment.
So Quentin, you have a question? Go for it.
Hi, Martin. Thank you. This was interesting. I was wondering, maybe you said it, but as a summary, how are the laser noise residuals comparing to the secondary noise for each of the 3 methods you talked about, like pseudo noise, and TDI ranging and TDI ranging with assisted tones?
Yeah, so I haven't looked at it numerically. So you mean those 3 cases, I believe?
Yes, I guess.
Yeah, and I think the only thing that I can say now, since I haven't looked at it numerically further, is that the laser frequency noise coupling is basically proportional to your error in arm length to the power of 2.
Okay.
So I guess it just scales.
Yes. Okay. And yeah, okay. and comparatively to the secondary noise, you don't know what is, you know, the difference with, for example, the first. Let's say to have an idea of, you know,
Yeah.
how it compares.
I mean,
Well, I can.
yeah.
No, maybe I can look at it somewhere, and then I can figure out with the the numbers that you have here.
Yeah. I mean,
We can have a Zoom call to discuss this further.
Yes.
It sounds like an interesting discussion for sure. Unless you have a quick one-line answer, Martin.
yeah, I guess I would think go for comparing it to the requirement that is
Yes.
given for the accuracy on your arm length. So how offsets on your arms would couple. And I'm not sure what number that is, but if you're below this number, you will cancel laser frequency noise, at least to this level.
Okay.
Say.
Yeah. Okay. Thank you.
Thanks for the question.
All right, wonderful, Martin. So thanks a lot. And we are only 10 minutes late around. So we have the last talk of the session, and that is going to be by Sam Francis. He is an optical engineer in JPL. So he left Australia to go to Pasadena, and he will tell us about, well, let's see. So you will tell us about uncorrected common mode delays for TDI. So we see your screen. Everything is
okay.
And we
Okay.
Yes, your presentation's up.
Great. Okay. Well, thank you. And thank you everyone for staying for this last talk of the session. So this work on common mode delays in TDI and how they potentially limit the laser frequency noise suppression was prepared with these co-authors. So there's a mix of recent research with John Baptiste and Martin, and then some historic research at JPL from about 10 years ago by Bob Spiro, Brent Ware, and Kirk McKenzie that we're building upon. So to give you an overview, we all know what TDI is, especially after hearing several talks about it in this session. But from my point of view, at a high level, TDI, the goal is to suppress laser frequency noise. And the way this works is the same laser frequency noise from our frequency stabilized laser is being measured at different times and points around the LISA constellation. And then in TDI, we're using measurements of the spacecraft separations to correct for the different delays in these measurements of laser frequency noise, applying synthetic delays and then forming combinations where the noise cancels. And so in this talk, I will be looking at an additional source of delays that is not corrected in the existing TDI algorithms. And so these delays are optical or electronic delays that are occurring after the beam splitter. So after the point where the lasers in our long arm interferometer are interfering. And so we're calling these common mode delays because they're common to both of the interfering lasers. So in the interferometer, we're interfering a laser that's traveled from the distant spacecraft and then one that's just propagated across the local bench. And both of these lasers have some frequency noise, and when they pass through the source of these common mode delays, they experience the same delay. And so this is distinguished from the spacecraft separation delays, which are differential. Only one of those laser frequencies sees that delay. Based on our estimates, this is likely dominated, these common mode delays, by photodetector group delay. This is a dispersive delay, meaning that it's going to be frequency dependent. And so I'll talk more about that later. So essentially in this talk, I'll go through and explain more about what we mean by common mode delays. I'll estimate their impact, describe some minor modifications to TDI that could be used to correct for them, and then discuss potential ways to measure them in orbit. Okay, so let's look at a simplified LISA diagram to just further explain what the difference between these two types of delays is. So this is just a simplified LISA based on the N1, 1-2 phase locking configuration. So in this configuration, down on spacecraft 1 at the bottom right, we have the laser 1-2 frequency stabilized. And for the purposes of this diagram, I've just simplified it to only show the hardware that's relevant for the measurement of the Michelson X combination. So in this measurement, really, we have one laser, this frequency stabilized laser in spacecraft 1, and we're sending along 2 interferometer arms to the distant spacecraft. With phase locking, that laser is then, or that laser frequency noise is then getting transponded back to the spacecraft 1. And so when we talk about differential delays, these are the delays that are experienced before the lasers interfere. So in this diagram, tau2 and tau3, which are the inter-spacecraft delays that we're familiar with in TDI, we would call these differential delays. And this is because if we look at the measurement of the laser phase noise on spacecraft 1 in this S12 measurement, we see the same laser noise, phi laser. This is the laser noise of our stabilized laser. But one is the prompt signal and one has experienced a different delay. So that's why we're saying it's a differential delay. Whereas the common mode delays, they're occurring after the lasers interfering. And so in spacecraft 1, as an example, we have this extra delay tau e, which could represent an electronic delay in this measurement chain of S13. And so in this measurement, we'd not only see the differential delay, tau3 from the inter-spacecraft travel of the beam, but both of these laser noises are now going to be delayed by an additional tau e. And so it's common to these two measurements. Okay, so like I said, these common mode delays are really any delay that's experienced after the lasers interfering. And so previously, people have talked about these types of delays, but they've focused on electronic delays. And this is fair because based on our estimation, electronic delays are going to be the dominant effect here. However, just to be technically accurate, we think calling them common mode delays makes more sense because really it is anything that's occurring after the lasers interfering. And so I've listed a few possible sources of these delays here. So optical path between the beam splitter and detector is one potential source of these delays. But I think in LISA, given the way the optical benches are built, and obviously between spacecraft, these optical benches are matched very accurately, this isn't going to be a big source of delay. Instead, we think it's probably the photoreceiver group delay, as I mentioned in the intro. But really, other sources could be things like the delays through the analog electronic front end of the phase meter, or even potentially things like filtering delays inside the phase meter. Okay, so now to really look at how these common mode delays would interact with TDI, I've got another little cartoon of how TDI is working. And so just in the top right of most of these slides, I've got a reminder of the locking configuration we're talking about for these particular analyses. In this cartoon, we're starting again with this phi laser. So this is the laser frequency noise of our stabilized laser. And in the Michelson, it's traveling along two arms, so arm 1 and arm 2. And depending on the arm lengths or how these spacecraft are moving relative to each other, these two arms will have different frequency responses. And so these boxes are meant to represent the frequency responses along the two arms. There's obviously shot noise added when we make the measurement, but that's not too important for this. What I wanted to show is that really in the simplest picture of forming the Michelson TDI combination, what we're doing is we're seeing these differential delays applied to the measurements of the laser phase noise. And then in post-processing down the bottom, we're introducing synthetic delays that are, for example, in the measurement of arm 1, we're applying an estimate of the arm 2 frequency response. And then in the measurement of arm 2, we're applying an estimate of the arm 1 frequency response. And by applying those two estimates and forming the difference, we end up with our TDI output, and this is removing the effect of those differential delays and canceling the laser frequency noise. So when we start talking about common mode delays, we're now adding an additional set of delays along these chains. And so here I'm representing these common mode delays by these boxes: measurement chain 1 frequency response and measurement chain 2 frequency response. So as I said, these delays could really be anything following the interference of the lasers on the beam splitter, but likely dominated by electronic delays. In this particular realization of TDI, these delays are not going to be corrected. So the only way they won't have an impact on the measurement we found is that if the measurement chain 1 and measurement chain 2 have the same frequency response. So if they have, the delays are matched between these two measurement chains. And for a lot of components in the phase meter, for example, and the optics, as I mentioned, these delays will be matched, but we think potentially in the photodetectors, they won't be. And so based on those diagrams we had, we estimated the frequency response of TDI to small differential and common mode delays. And so on the left, this little equation is showing the ratio of laser frequency noise to shot noise post TDI. So we think for TDI, to determine how successful it is, really, we want to look at how big the laser frequency noise is after TDI and compare that to how big the shot noise or secondary noises are after TDI. And so through this ratio, we see that for a differential delay error tau epsilon, the frequency response is flat. So it's this blue line down below. So basically that means that it's really just the error is going to be linearly dependent on the size of the error we make in our estimation of the delay. Whereas the common delays enter a different way. We end up with this sinusoidal dependence on frequency for a similarly sized delay. And I'll just point out that this is, well, this lower plot is actually a plot that Bob Spiro showed at a MAUD 8, 2009. And a lot of this analysis was initially inspired by this LISA frequency control white paper, also from 2009. So for anybody working on TDI now, I think if you haven't seen this paper, it's actually still very relevant to a lot of the discussions and has a good look at a lot of the practical sides of TDI. So I'd recommend checking it out. And there's a link to the paper on Atrium, which hopefully you can follow if these slides are made available at some point. So we wanted to understand how big this delay, the effect of this common mode delay would be. And so the best way to do this would be to look at the LISA system and the LISA instruments and perform measurements of the delays through them and check how consistent they are between the different boxes that are built. We didn't have access to this, so instead what we did is look to the literature, and from a paper on photodetectors, we looked at estimating the group delay of the photodetectors based on some fits to data in this paper. So paper reference down here. And so the reason the photodetectors are potentially going to be the dominant source of these common mode delays is that these photodetectors by design are limited bandwidth. So we only want to allow 2 to 25 megahertz really for the heterodyne frequency. And so the bandwidth of the photodetectors is only going to be slightly larger than that. And when we have something that has a limited bandwidth, you often introduce some group delay through that filter or through that photodetector that has a frequency dependence. And so this is the idea of dispersion, which effectively means that as we're changing the beat note frequency that we're measuring with this detector, we're going to get a different delay through the detector. And so this plot, which, as I said, is just a fit to some data, so it'd be really interesting to see what the real data looks like. But from this plot, we can estimate that for a beat note frequency from 2 to 25 megahertz, we're getting a group delay change of roughly 3 nanoseconds. And so running with this number, thinking, okay, well, we can potentially get 1 nanosecond common mode delays through these photodetectors. We ran some simulations to look at the impact of this type of delay. And so this is using LISA simulation. The plots I'll show are from a very simplified version. So we're only using laser frequency noise. And again, we're using this locking configuration that has some nice symmetry in it that allows us to just look at this Michelson X. And also we're using equal and static arms, at least for these 2 plots. So what we see here is effectively when we introduce one of these common mode delays, which is the green curve, here I'm considering a common mode delay of 1 nanosecond that isn't corrected. And I'm looking at the residual frequency noise in the Michelson combination. And what we see is that a 1 nanosecond common mode delay is equivalent in magnitude to a 1 nanosecond error in the estimation of the differential delays or the inter-spacecraft ranging measurement. So that's comparing the red and green, a similar size magnitude. So a 1 nanosecond error in common mode delays is equally as important as a 1 nanosecond error in our PRN ranging. Although there is a slightly different frequency response, which is due to the math, I guess, I showed on a few slides. So I also mentioned that if things are matched, so if we have the same common mode delays, then everything goes away. And so this is just a very simple and boring plot to confirm that, at least in this symmetric locking configuration, if we now consider the picture down the bottom left, where both these measurements on spacecraft 1 have the same tau e common mode delay, everything cancels and we don't need to worry about these delays. So really, the next part is concerned with what happens if we can't guarantee these delays are equal on the 2 sides of the spacecraft. And I think based on the frequency planning for where we expect beat note frequencies, or how we expect beat note frequencies to evolve over the mission as the arm lengths are varying, there will be times where along one arm, it will have a different heterodyne frequency to the other arm, which, if we have this dispersive effect in the photodetector, would introduce different common mode delays in the 2 arms. However, we think that these common mode delays could be corrected with very minor changes to the TDI process. And so this diagram again is showing that really all you'd have to do to correct for these delays is add this yellow box here, this step right before applying the synthetic delays for TDI. And that's just undoing the measurement chain delays in measurement chain 1 and measurement chain 2. And so this sounds easy, but obviously the complications then would be, how do you know what delays to correct for? And so there's probably several ways this could be approached. So one way could be performing ground-based measurements or calibrations pre-launch. and understanding what type of delays we expect to get through these systems and how stable they are. If it turns out we think they might not be stable over time or over different temperature ranges, then something that Martin mentioned at the end of his talk just now is that we're also considering how adding some tones into the laser frequency might be able to help us disentangle the differential and common mode delays. And so the idea that we want to investigate now is that possibly with the two tones that Martin used in his analysis, maybe we have enough information to measure these common mode delays as well. But maybe we need a third tone to do it, to really disentangle and measure all the degrees of freedom. But this would work on a similar way to the tone-assisted TDIR that Martin explained, which is we know ultimately the goal of all of this is to suppress the laser frequency noise. And so if we have these tones on the laser frequency noise, that's giving us a really strong signal with good SNR, signal to noise ratio, to suppress and minimize. And we can adjust the time of flight delays, our estimate of the interspacecraft range, as well as our estimates of these common mode delays, and refine everything until we're at a level where the laser frequency noise cancels to what we require. And so this is just a very quick flashback again to like 2009 when Bob Spiro talked about some of this. So we found on the JPL LISA testbed, which is this testbed used for experimental demonstration of TDI, that we do see these common mode delays. It was found that to get the best laser frequency noise suppression, a 23 nanosecond delay was needed in addition to the other TDI delays they were using. And the lower right plot is just showing that as this
Sam?
delay, yep.
Just interrupting you to give you a heads up that you're actually 2 minutes over the 20 minutes. So if you can wrap up quickly, that's and don't worry, we will leave the room open. So yeah, I see there's 2 more slides. If you wrap up, then we can.
Yeah, okay. Luckily, the end slide is the conclusion. So yeah, so the last point here is that we saw this dispersive effect. Conclusion, I don't need to go through this. We've all heard it. So we're looking at these common mode delays, and really the future work is we're continuing these simulations and trying to understand particularly what happens when we start looking at configurations without this symmetry. We want to study, can we disentangle these delays by using these tones? And then also potentially once we start thinking about phase locking between spacecraft, are any of these electronic delays or common mode delays going to be a problem there? Okay, well, thank you very much, and sorry for running over time.
Thanks, Sam. That was a very interesting talk. I was just curious actually about the, okay, I see Olaf has raised a hand, but I was curious about, so this is purely data analysis for common mode laser noise reduction. Have you thought about how this is feasible in practice? So have you designed with FPGAs and lasers and whatever else is necessary in experiment to verify the data analysis actually you've done?
Yeah, I suppose some of the initial thoughts came out of those JPL LISA testbed experiments, which were, it's an optical testbed with FPGAs, FPGA phase meters measuring the laser frequency noise. And it was found in those results, or in the analysis of the data taken there, that these additional electronic delays were needed to be accounted for. In terms of developing algorithms or anything to deal with it, it does just become a post-processing thing, provided we're able to measure the delays or have some idea of how big these delays are. It's just an additional post-processing step.
Thomas, do you have a comment to that?
Not really, no.
Okay, no problem. So yeah, Olaf, you have a question?
Yes, thanks for the interesting talk. I had two questions actually. One of them, you say that the photodetector dispersion you think is the dominant effect. Do you think that's something that can be well characterized on ground before the flight, such that we could, since we know the beat note frequency of each beat note, we could simply apply a known correction?
Yeah, I mean, that would be an ideal way to do it. I suppose our estimate is really just like a fit to some data in a paper. So I think the thing to do would be the people working on the photo detector would want to characterize this and understand how repeatable it is between the different photo receivers that are built. And then are there things like temperature effects that are going to change this in a significant way? And so I think we have to decide, what's the maximum allowable variation in these delays, and then decide if we're stable at that level given the thermal environment that these detectors will be in.
Okay, makes sense. The second part was that you said if you introduce more calibration tones for your TDI tone assisted TDI ranging, that you would be able to disentangle common mode and differential delays. I was wondering, is that actually needed to disentangle these two components to do the laser noise suppression? Because in the end, you apply one delay to each time series, and
right.
Do you need
yeah,
do you need to know what is common mode, what is not common mode, because you delay each time series once? So I would think that it's enough to know the total delay that you need.
I think it's to do with so you're saying like in TDI, you're already delaying these time series. And so really you're suggesting that maybe you can just like treat all delays as like a single delay and just correct for that. And you're measuring that with the tones. Is that what you're suggesting?
Yes.
Yeah, so I guess from our understanding, like the fact that they have this different frequency response, TDI has a different frequency response to these tones, to these delays, whether they're the differential or common mode ones. We think that means that treating them as a single delay doesn't necessarily correct for them. Like our analysis suggests they really do need to be like treated separately.
Okay, interesting.
But yeah, that's something we really want to study, and I think Martin's results have been really good. So hopefully building from there isn't too difficult.
Okay, thanks.
Well posed questions. Thanks, Olaf. And I think we should formally conclude the last data analysis session. I think we exhausted the TDI data analysis pretty well in this session. So I want to thank Quentin, Martina, Olaf, and Martin, Sam, and Mauro for this session and making it lively and engaging with the recent developments in TDI. So with that, we conclude the session formally. So if you're hungry like me, go get dinner before, or food before the plenary starts at 8 CEST. Otherwise, I think we can leave the room open for further discussion if you want.